My name is Yasser Lamalem and I am a PhD student at Faculty of Science Ibn Tufail Kanedha. I am here on behalf of my co-authors Professor Khalid Housni and Professor Mohamed Benaddy. I am here to present our paper that's called A New and Fast Algorithm to Enumerate All Minimal Pairs starting from the source node S and the sink node T at the same time. Our planning today is first an introduction of the area and then to the end of the proposed algorithm in this paper. Second of all, we have definitions and some functions that are going to use in the proposed algorithms. Number 3, we are going to explain the algorithm. Number 4, we are going to give an example and we are going to show the execution time of this example. Number 5, we have a conclusion. The IEEE 90 standard defines the reliability as the ability of a system or component to perform its required functions and the stated condition for a specific period of time. Reliability studies have been sadly neglected in the past. This might have been because the period of a system utilization was much less than the probable time to failure. However, design of the sort are uneconomic and cannot be permitted these days. For that, there is so much at stake, in terms of cost, human life and security, to take any risk with devices which may not function properly when needed most. The study of network reliability is one of singular importance due to its clear applicability to computer networks, communication systems, and distributed systems. Major network failures are essentially of two types: node failure due to equipment breakdown or equipment damage resulting from an event such as an accidental fire, flood, or earthquake. Link failure due to inadvertent fiber cable cut despite increased network care and maintenance efforts. The link between one telecommunication office or computer server and the other still fail frequently. A lot of the algorithms presented in the literature start with the source node S to find all paths to the sink node T. In this method, an efficient enumeration algorithm which generates all minimal paths is a general network is presented. This algorithm is based on finding all minimal paths starting with the source node S and the sink node T at the same time. At each iteration, instead of progressing at each time by one edge, as in the algorithm of the literature, we progress by two edges, one from the source and the other from the sink. Now we have some definitions and some functions. A graph. A network can be represented in a form of a graph G, where V is the set of the vertex of nodes or nodes, and E is the set of edges or arcs. We denote by NV the number of vertices and by NE the number of edges. A path. In a graph theory, a path in a graph is a finite sequence of edges which connect a sequence of vertices. What is a minimal path? A minimal path in a graph is a finite sequence of edges which connect a sequence of vertices which are all distinct from one another. Now we have functions. We are going to explain some 5 functions that we are going to use in our proposed algorithm. First, we have a function that's called link that accepts 2 arguments. The first argument is a node called node 1 and the second argument is a node called node 2. This function check if there is a link between the two nodes, node 1 and node 2, and return true if it's the case. The case where it is a link between the node 1 and the node 2, or if node 1 and node 2 are the same node. Otherwise, it returns false. Then we have a function that's called createPath, which accepts 4 arguments: node 1, node 2, and prefix and suffix. Prefix and suffix are 2 sets of nodes. Create a path by concatenating the prefix, the set prefix, and node 1, node 2, and the inverse of the set suffix. For example, let's node 1 equal to node number 2, and node 2 is the node number 3, and the prefix containing the node S, the source node S, and the node number 1, and the prefix and the suffix contain the sync node T and the source number 4. The path that will be generated is S1, 2, 3, 4, and T. Now we have two functions. The first function is called successor, that accepts the same argument as the function create path. Return all successors of node 1 that do not belong to the prefix or suffix and are different from node 2. The second function called predecessor that accepts the same argument as successor, function successor. Return all predecessor of node 1 that do not belong to prefix or suffix and are different from node 2. Then we have the last function that's called get combination that accepts two sets, set 1 and set 2. Return all possible combination between set 1 and set 2 in order 2. In other words, the get combination set 1 and set 2 returns. For example, if set 1 contain number 1 and number 2, nodes number 1 and number 2, and the set 2 contains the node number 3 and number 4, then the possible combinations are a set that contain number 1 and number 3, a set that contain number 1 and number 4, and a set that contain number 2 and number 3, and a set that contain number 2 and number 4, or possible combinations. Now we have to explain the proposed algorithm. The basic idea of the proposed algorithm is to traverse the graph at the same time from the source node S to the sync node T, instead of starting only from the source node S or node T. This technique will allow us to reduce the execution time because at each iteration, instead of progressing at each time by one edge, as in the algorithms of the literature, we progress by two edges at the same time. The initial parameters of our algorithm are the source node, the sync node, and the two empty sets, prefix and suffix. The prefix is the subpath linking the source node 1, and the suffix is the subpath connecting the node 2 to the sync node T. Node 1 or node T is the laced node of traversal that starts from the source node or the sync node. At first, the algorithms check whether node 1 and node T are identical or connected by an edge. We are going to use the function that's called link. If so, the algorithm has found a path, so the create path function will be called to create the path using node 1, node 2, and the prefix and the suffix. If node 1 and node 2 are identical, there is no more recursive subcalls. Otherwise, the algorithm produces the other candidates nodes that will be used as a new parameter for the next recursive call. To generate these candidates nodes, we used the two functions successor and predecessor. The nodes that generate will be stored respectively in set 1 and set 2. Now that we have generated the two sets of nodes, we test if at least one of them is empty. If so, there is no more recursive subcalls because there will be no other candidates for node 1 and node 2. Otherwise, this function get combination will be called to construct all possible combinations. Each combination will be used to make a new recursive call. As we can see here, this is our algorithm. Now we have a comparative study of the algorithm. In this section, we compare our algorithm with the fastest algorithm in the literature, Gangan-Bay algorithm. In this experiment, we have used the grid network. A typical grid network is shown below. In each experiment, we incremented the number of edges and nodes. Now we have a table that contains 4 columns. The first column is a network, and in each rows we increment the number of edges and the number of vertex, the number of nodes and the number of vertex. The second column contains the number of minimal paths found by our algorithms and the Gangan-Bay algorithm. The third column contains the result of execution time for our algorithms, and the fourth column contains the result of a gang-by algorithm. As you can see here, our algorithm is two more fast than the gang-by algorithm because our algorithm is starting from the source node S and the sink node T at the same time, but gang-by algorithm is only starting from the source node. As a conclusion, in this paper we have given a new method of enumeration of minimal paths in a graph. Our method consists of traversing the graph on both directions, from the source and from the sink. This decision to traverse the graph in both directions has allowed us to reduce by half the number of the tests required to find a given path. According to tests we carried out, the proposed algorithm is very fast compared to the other algorithm in the literature. Thank you.